Welcome, Differential Equations class. Today we're going to do lesson 23, reduction of order. And the question of the day is if we were given a differential equation and one solution, could we find another? And the answer is yes. In fact, we've already done it. We did it back in lesson 20 when we had that repeated solution. Then we found another solution. And so can we generalize that for any differential equation? And so I see this being in two videos, one video kind of showing what's going on, and then a second video doing an example or two. So once again, suppose we were given a non-trivial solution of a differential equation and we want to find a second one that's linearly independent. So let's remember that linearly independent means that if I take one and divide by the other, I get something that's a non-constant. Or another way of saying that is some other function of x. Let's call that u. So y sub 2 is going to be this some function of x times y sub 1. Let's see how that helps us. Let's just go ahead and do an example. I think these are easiest to see as an example. So if my first solution is x squared, and it is one solution of the differential equation x squared y double prime plus 2x y prime minus 6y equals 0. Let's find a second solution. I strongly encourage you guys to get out a sheet of paper and follow along. Don't just watch and assume that you'll understand it, or you may understand it kind of superficially, but if you sit down and you write it out, you'll be much more likely to have it make more sense. So okay, we have this one solution that they've given us, and so when we've said up here that the second solution is going to be some function of x times that first solution. So my second solution is going to be some function of x times x squared, or to kind of simplify it out, because we're going to have a lot going on, u x squared. So like a lot of other things, we're going to go ahead and take this and plug it into our differential equation. So of course, in order to be able to plug it into that differential equation, we need the first and second derivative. So let's go ahead and find that. So the first derivative of the first, leave the second alone, plus, derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. Second derivative of the first, leave the second alone, plus leave the first alone, times second derivative, and that's just of this first term. So let's go ahead and do it again for the second term, plus derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. We can go ahead and, we have like terms there, so let's go ahead and combine those. Okay, so as we said, we're now going to go ahead and take both of those and plug those back into our differential equation. This is going to be a little bit long, so let's see if we can do it. X squared times u double prime x squared plus u single prime 4x plus 2u plus 2x. Now go to y prime. So we've got u prime x squared plus u 2x, and then minus 6, my original one, which was u x squared, and that should equal 0. Well, that wasn't too bad. Okay, let's see if we can simplify it. What happens when we simplify that down a little bit? Oops. U double prime x to the fourth plus u prime 4x to the third plus u 2x squared plus u prime 2x to the third plus u 4x squared minus 6u x squared, or let's keep everything kind of in the same, u 6x squared. So I have the u's always first, because that's how I'm going to collect like terms. And so if I look here, I've got, this is my only u prime. Let's go ahead and bring that, or double prime. Let's go ahead and bring that down. Now let's look at single primes. I've got a single prime, oops, come on, a single prime here, a single prime here. I think those are my only two single primes. So when I combine those two terms, oh look, and my powers of x are still the same. So that would be a single prime 6x to the third. And now let's look at just the u's. Here's a 2x squared plus 4x squared minus 6x squared, so that's kind of nice. They all cancel out. That one cancels out with that one, which cancels out with that one. So it looks like that simplifies down just to this. Well, that's kind of nice. Okay, so now as the name of the process states, it's a reduction of order. And so we want to reduce the order through substitution. Reduce the order through substitution. And normally we would do a u substitution, but we've already used u. So let's let w equal u prime. If I let w equal u prime, then w prime would be u double prime if I take the derivative of both sides. So sticking that in, we now have, I'm gonna switch these orders just because. So now if I switch these orders, I've got x to the fourth w prime plus 6x to the third w equals 0. Well, it may not be that easy to see, but this is actually a linear first order differential equation. And so going back from the beginning of the semester, we have a process for that. So the first step of that process is to get rid of this coefficient here. And so how do we get rid of this coefficient? We divide by that coefficient. So now we've got y prime plus 6 over x w, not y, w prime plus 6 over x w still equals 0. We find an integrating constant. So if we integrate that, we have natural log, 6 natural log of x. Remember, let's make that into a power. And so this now becomes x to the 6th. I go and I multiply that there. So now I have x to the 6th w prime plus x to the 6th times 6 over x w equals 0, where this one becomes x to the 6th w prime plus 6x to the 5th w equals 0. And remember, for linear, we say, okay, well look, that's just the product rule. So let's rewrite that product rule. The product rule would be a derivative, in terms of x, of these two functions, x to the 6th times w equals 0. So next step here would be to take the integral of both sides with respect to x. And so now the derivative and the integral are just opposites, so they cancel each other out, and here we get a constant. But, oh, let's solve for w. Solve for w. So w is cx to the negative 6. However, our problem wasn't in w's. Let's substitute back into u's. Back, not by, back. So we said that w was u prime. So this is actually u prime equals my arbitrary constant x to the negative 6. So let's figure out what u is. So again, we're going to integrate. And so we've got u equals some integrating constant. Add 1 to my power, divide by that power, and then plus a new, we now have a second integration constant. Okay, but at the beginning of this whole process, beginning, double ends? Yes. We said that the second answer was this u times the first answer. So for us in this particular problem, that means our second answer has to be this u value that we just found. Actually, let me back up a step. So this is going to be just a different, another c. Let's make it another arbitrary constant. Let's make it c3. So we've got c3 x to the negative 5th plus c2, and that's going to get multiplied by our original answer, which we said was x squared. So we now have c3 x to the negative 3 plus c2 x squared. So this is called my family of solutions, which I believe is also called general solution. And this, if you notice, is the given solution. And so that makes this one right here my linearly independent second solution. So y sub 2 is going to be x to the negative 3. Nice. So, nice. This is a big, long process. It's a big, long process to go through every single time. So if I did this generically, I'm going to do this in blue. Or red, blue. Okay. Generically, we can get a formula. And so if we have some function of x with the second derivative and a different function with the first derivative and a third function with y, and it equals another equation of x, and we know that my second answer is some function of the first answer, then Ready? It's a big long formula. Oops, nope, not equals. Remember, we did the integral twice, so expect two integrals in here. Negative f1x over f2x dx over y squared 1 dx. Woof! So that's our big formula. So instead of going through the process, we can go through this formula. In the next video, I will be doing just that.